तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We shall begin with a brief recapitulation of what we had been doing in the last class, that is the switching aspects of an inverter circuit. Okay. So, the circuit which we have been discussing is quite familiar by now, is given here. So, you have a base resistance, a collector resistance, and you have a supply voltage, and you have, this is the input point and this is the output point. Okay. And in this circuit, suppose you apply a voltage waveform of this type, okay, that is it goes up to, this is a forward voltage Vf, okay, and then you have a reverse voltage Vr. Okay. Then what is the sequence of events which happens? That is what we are interested in. Now, what is going to be the base current waveform? That is the next thing of interest. IB, okay. We have seen that the IB at this point you can assume it to be almost a constant, okay, and again here, you know, it remains a constant, reverse base current flows, and then finally it goes to 0. Okay. This is the waveform which we have. Okay. Let us call this we have called this IF, the forward current, and you have a reverse current, okay, IR. Okay. Now, you know that IF we can write is nearly equal to Vf by Rb, okay, and IR is nearly equal to Vr by Rb. That is because we assume here again that the input voltages, that is Vf and Vr, their magnitudes are much greater than the base emitter voltages, okay, because the base emitter voltage in this period, okay, is going to be very small compared to this input voltages. Okay. Only after at this point in time, you know, when the base charge has been completely discharged, the base emitter voltage tends to become sufficiently negative, and so the base current, reverse base current falls. Okay. So, with this assumption, if we now take up the base current, base charge, if we plot the base charge, okay, we have also seen that. Okay. What happens is, in this period, all right, the base charge, the base gets charged, all right, it builds up, okay, and then when the input voltage goes negative, the base charges are removed, okay, all right. So, it basically goes to 0 here, all right. Now, we have also how do you calculate these base charges? Okay, what is the relation governing this? That we have seen the familiar relation IB is equal to QB by tau n plus dt. Okay. You get this nature of this base charge variation, okay, if you solve this differential equation, all right, for QB, okay, and of course you have to take the proper initial conditions, okay, and then you get this nature. We have already done that, okay. Of course, what it means is when it is forward current is flowing, okay, then in the steady state once it reaches here, okay, this goes to 0, IB is equal to IF. So, QB is equal to IF tau n, okay, and then so this is the peak value and then it goes down, all right. Now, if you plot the collector current, okay, what happens is when the base charge is building up, okay, the collector current also builds up, okay, but then it reaches saturation. The base charge when the collector current reaches saturation is given by IC sat into tau t, okay, where tau t is the transit time, okay. So, this is the value, okay, say when the transistor reaches saturation, okay. So, if you plot it here, you know, drop this line here. So, the collector current keeps increasing here, okay, reaches saturation, all right, and then although the base charge keeps building up, the collector current has saturated, okay, that is governed by the circuit, okay, it cannot build up any further, okay. So, it becomes a constant, okay. At this point the base current has reversed, okay, but still the collector current is in remains at the saturation value, okay, till the base charge falls down to IC sat tau t, okay. So, the collector current will remain in the saturation value up to this point and then of course it will discharge, all right. So, these values, okay, so you have we should say 3 components of delay here, okay. One is the on time, this is the on time, okay, we may call T on, that is the time required for the current to reach the saturation value once after you have applied a forward voltage at the input. Then while switching off there are 2 delay components, okay. One is called the storage delay time, this value TSD, okay, that is the time required for the transistor to come out of saturation after you have applied the reverse voltage, okay. And then there is another component which is the discharge time, okay, that is it comes out of saturation, but finally what you have to do is you have to switch off the transistor has to go to cutoff, all right. So, what is the time required to from the transistor to go from saturation to cutoff, that is called the discharge time. So, this is the discharge time, okay, TD, let us call it TD. So, you have the various relations, okay, T on, we have already seen that relation, tau n ln, what is the relation, 1 by 1 minus IC sat by beta into IF, okay. So, this is the time required for the transistor to turn on. Then you have the storage delay time. So, that is basically what you do is you solve this equation, we have already done that, and then you see what time it requires to go to these values, okay. Storage delay time, we have also seen that tau n ln you have IF plus IR divided by IC sat by beta plus IR, okay. Then there is the other relation, we did not put it down last class, but I think you can very well do it yourself, okay. It is very simple, it is given by tau n ln 1 plus IC sat by beta IR, okay. IR of course is actually the modulus of current. IR is a negative current, but that is what we are interested is in the modulus. So, you have these 3 components of delay, alright. Okay. So, these are the different relations. So, given a particular circuit, okay, you can very easily calculate if IC sat, alright. Also, if IF and IR given the input voltages from the relations for here IF and IR, okay. You can, if you know IF and IR, you know the beta of the transistor, you can calculate the different delay components, okay, of the particular circuit. Is it clear? It is not very, it is very simple. Now, let us take a particular example, just give you an idea of what is the values of the delays, alright. So, let us take an example, let us put, I shall take a particular problem here. VCC is equal to say 5 volts, RC equal to 1.5 kilo ohms, beta is equal to 50, and say tau n is equal to 10 nanoseconds. Okay. Now, if you just put these values, you can calculate all these things, okay. And if IF say is equal to 1 milliampere, okay, T on works out to, I just put down the results, you can just to give you an idea of the different delays, works out to 0.66 nanoseconds, okay. Okay. If IR is also equal to 1 milliampere, okay, TSD will be equal to 6.31 nanoseconds and TD will be equal to 0.62 nanoseconds. Okay. All right. Now, in case IR is equal to 10 milliampere, TSD is equal to 0.89 nanoseconds and TD is 0.064 nanoseconds. So, what comes out of this? Okay, if these calculations, number one, okay, if you look at it, the reverse current is very important. How much reverse current is flowing, because it is the reverse current which is actually pulling out the charges. Excess base charges is pulled out when a reverse current flows. Okay, so, the larger the reverse current, the faster is the removal of the excess base charge. Okay. So, you can see here the storage delay time is the major component of delay, okay, and of course, with increase in the reverse current, the storage delay time reduces. Okay. So, it is very important to be able to reduce the storage delay time, okay, because see the charges are very large, okay, when you go above saturation, okay, there is a lot of excess charge, okay, and that has to be removed. So, that takes a lot of time. So, this is the just gives you an idea, okay, of the delays, okay. That is very important to have large reverse current to reduce the delays. To reduce the delay and among which and of the delays the storage delay time is the major component, alright. And of course, the storage delay time occurs when the transistor goes to saturation, okay, alright. So, this is about the different delay components. Before going ahead, one more point, okay. In addition to these delays, okay, we have actually neglected another component of delay, okay, which is due to the junction capacitances. Okay. These are all the stored charge delays, okay, delays due to stored charge. But when you are changing the voltage across a junction, there is a capacitance. So, that capacitance also has to be charged and discharged. Okay. So, there is also going to be a delay due to that. All right. So, basically for the delay due to the junction capacitances, you have basically I think delay due to junction capacitance. Okay, you can look at it, okay, as a circuit like this. You have a resistance, okay, and you have a capacitance. Okay, that is the input capacitance. All right, you have an R and you have a C, okay, at the input say, and you are applying a voltage like this. All right, so the voltage across the capacitance must change. All right, so so it is finally going to the steady state. All right, now the delay, okay, depends on the RC time constant, correct. So the delay depends upon the RC time constant. The larger the RC time constant, the larger is the delay, okay, and you can very well calculate that. Okay, it's not very easy to calculate, provided, okay, you make an assumption. See, this input capacitance is actually a junction capacitance which we are talking of, and the junction capacitance is not a constant capacitance. Okay, it depends on the voltage across the capacitance, which makes it a very difficult problem to solve, isn't it, because the capacitance itself is continuously changing. Okay, but for all to simplify the problem, we usually replace this input capacitance by a average capacitance, okay, we call C effective. Okay, C effective. See, it also includes in this circuit, okay, it includes not only this base emitter capacitance, okay, that is junction, but also you have the base collector junction capacitance, which has to be reflected on the input side. You know how to do that, Miller effect, I think you are aware of that. So basically you have an input capacitance which has to be charged. Okay, so now you can easily calculate that. Okay, for example, if you take a small particular case, that is input, if the voltage across C effective changes from 0 to V on, say, okay, all right, that is when you are charging the input. Okay, it changes from 0 to V on, say the voltage across this, and you have applied a voltage Vf, okay, here. So you can solve this very easy, okay, and you will get the T on will be equal to R C effective ln 1 plus V on by Vf. Of course, the assumption here is that V on is much smaller than Vf. Okay, if that is the assumption, you get this. Basically, the idea is it is going to be proportional to RC time constant. Okay, so you have these two components of delays. All right, the one due to the stored charge, which is actually the diffusion capacitance which we are talking of. All right, we have already seen there are two types of capacitance: diffusion capacitance or stored charge capacitance, and the other is the junction capacitance or the depletion capacitance. Okay, all right. Now there is a basic difference in the two types of capacitances. Okay, the effect of the two types of capacitances, which we shall see here. See, if you look at this circuit here, okay, come back to this circuit. Now, if we increase both RB and RC by the same amount, suppose we increase RB and RC by the same amount, same factor, all right, what happens to these delays due to the diffusion due to the stored charges? If you look at these expressions now, say T on, what happens to, see, you have a IC sat by IF, all right. Now, if what happens to IC sat if you increase RC? It reduces, okay, and IF, because you are increasing RB, it also reduces. It reduces by the same amount if you are increasing both the resistances by the same factor, all right. So what happens to T on? It remains the same. What if you take up T as D, this relation, okay, stored charge delay, okay, again, see, both I mean the numerator and the denominator would change by the same amount, okay, if you change RB and RC by the same factor. Okay, so IF and I, if you increase RB, okay, both IF and IR would reduce. IC sat would also reduce if you increase RC, and IR would also reduce. Okay, and if the change in the resistance values is the same factor, okay, this factor remains constant. Okay, no change in TSD, even TD. Okay, IC sat by IR remains constant. So, in this circuit, if you change the values of resistance, all resistances you increase or decrease, okay, by the same factor, the delays due to the stored charge component does not change. All right. That is because, you see, again you come back, if you consider them as some capacitance, okay, RC, okay, time constant, okay, the diffusion time constant, the RC time constant due to the diffusion capacitance. All right. Now, the diffusion capacitance is proportional to current, okay, and current is inversely proportional to resistance. Okay. So, what is RC time constant going to be? That is independent of R change, okay, because if R goes up, capacitance goes down because the current goes down. Okay. So, RC time constant does not change, okay, independent of the change in resistance, okay, that is diffusion capacitance. Okay. But if you look at the junction capacitance expressions, okay, T on, okay, it is RC effective and C is independent of the currents. So, if you increase R, the delay is going to increase. All right. So, these are the two basic difference in the nature of the two delays. So, suppose the resistance values in the circuit are very high, say, all right. So, what is going to happen? This the delay due to the junction capacitance is going to dominate, all right. And then if you go on reducing the value of the resistances in the circuit, this delay is going to go down, whereas the delays due to the stored charges is constant. Okay. So, if you keep on reducing the resistances in the circuit, okay, the delays due to the junction capacitances will slowly reduce, and finally, the delays will be determined by the stored charges. Okay. So, if the resistance values are very high, it is the junction capacitance, delays due to the junction capacitance which is dominating, or you can look at other ways, if the current levels are very low, it is the junction capacitance delays which is dominating. But if you increase the current levels, okay, all right, or by reducing the resistances, all right, then it is you are reducing the delays basically, because the diffusion capacitance is constant, delays due to diffusion capacitance is constant. So, you are reducing the delays, and finally, it becomes determined by the delays are determined by the stored charge delays, which is a constant, it does not change after that. Is it clear now? And that delay which you finally arrive at, which is the lowest delay in the circuit, okay, I mean, all right. So, basically if I just plot it, you know, if I just plot it as a versus current, you know, the delays, okay, it will go down with increase in current, okay, because the junction capacity, this is the delay due to the, say, the stored charge which is a constant. Okay. So, finally, it will go down and then it becomes a constant like that, all right. If you go on increasing the current, okay, so it is going to become determined by the delays of the junction, the stored charges. Is it clear? And what is this stored charge capacitance? Mostly determined by the storage delay time. Okay. So, if you want to increase the maximum speed at which a circuit can be operated, you have to reduce the storage delay time. Okay. All right. That is very important. All right. So, you can go on increasing the current on a circuit, but finally, the delay is initially the delay will fall, okay, but finally, it does not change any further, okay, because the delays due to the stored charge becomes independent of current, So, in order to increase the speed of this circuit, we have to find mechanisms by which this stored charge delay must be reduced or eliminated if possible. Okay. the way to do it is to see that the transistor does not go to saturation. Okay. If the transistor did not go to saturation, all right, then the stored charge delay is eliminated, isn't it? Okay. Now, how to do that? Now, if you had a circuit, for example, where you see if you apply, when you apply a forward voltage, what happens is the transistor output, you know, the collector emitter voltage is going to drop as you go on increasing the base current, we have seen that, and when it reaches saturation, VCE becomes equal to around 0.2 volts. But suppose you had a circuit by which, you know, just when it was approaching saturation, okay, then the base charge storage, okay, it would stop, all right, it would stop, you know, by some mechanism. That would be an ideal case, all right. Now, well, that is really achieved in a class of in a special type of bipolar transistor called a Schottky transistor. I will just tell you what it is. Okay, this is called a Schottky transistor. Now, we have already seen what is a Schottky diode. Okay. What is a Schottky diode? A Schottky diode is a metal semiconductor junction, okay, which has rectifying properties, all right. And the property of a Schottky diode in comparison with a PN junction diode is that the cut-in voltages are much lower. Okay. That is it in the forward conduction mode. Okay. The current, it starts conducting at a much lower voltage. Okay. For example, I will just draw this again, that if you have a PN junction diode, characteristics like this, IV, the Schottky is going to be something like this. This is a Schottky. Okay. So, it starts conducting at a much lower voltage. Okay. So, suppose if this is 0.6 volts, say this may be 0.3 volts, all right. Okay. So, that is the difference between a Schottky diode and a PN junction diode in terms of characteristics. Now, that is utilized in a Schottky transistor. Okay. A Schottky transistor is something like this. You have a normal transistor, say, okay, and between the base and the collector you have a Schottky diode, all right. Now, what happens? Suppose if you look at this transistor, okay, what happens in the circuit, okay, is that in order to drive this transistor to saturation, what you do is you increase the base current, and as the base current is increased, the collector voltage drops, okay, and what happens is that this transistor, as the collector voltage drops, the base collector junction gets forward biased and the transistor goes to saturation. Okay. Now, in this case, say when this collector voltage is falling, okay, suppose this collector voltage is 0.3 volts less than the base voltage, what is going to happen? This Schottky diode will start conducting. Okay. For example, let us say this base voltage is 0.7 volts, okay, and this collector voltage is falling because you are increasing the base current, and when it reaches say 0.4 volts, all right. Okay, what happens is this diode starts conducting, and then the base current, okay, which was flowing into the base, the excess base current, okay, will start flowing into the Schottky diode, and there is a conduction path from here to here. Okay. That is, it flows through the Schottky diode into the collector. Okay. And this, you know, in a diode, once it starts conducting, okay, it is a very steep characteristics. Okay. The voltage is almost clamped to that value. all right. So, this is almost clamped at 0.3 volts, okay, all right, maximum 0.4 volts. Okay. So, this voltage, the collector voltage becomes clamped to around 0.4 volts, or maybe it may go down to 0.3 volts, okay, but it cannot go down below that. Okay. And this is actually serving as a bypass path for the excess base current, okay, and the base charge cannot build up any further, all right. So, this actually prevents the transistor from going to saturation. The transistor does not go to saturation, it goes to the edge of saturation and then it gets clamped, okay, the output voltage gets clamped, all right. So, when you have a transistor like this, okay, called a Schottky transistor, the symbol for this transistor, okay, is this. This is the symbol for a Schottky transistor. Okay. So, when I draw like this, all right, it actually means that this is a transistor with a Schottky diode between the base and collector. This is called a Schottky transistor, and this transistor is not going to go to saturation, all right, okay, because of this Schottky diode will start conducting when the transistor goes to the edge of saturation, okay, and obviously this transistor will not have the storage delay component, okay, which is going to make it a faster device. Is it clear? All right. So, in the circuit, if you replace a normal transistor with a Schottky transistor, you get this improved performance in terms of speed. All right. Now, okay, it is a very good concept, all right, you have a Schottky diode between the base and collector, but how do you realize it? Okay. Technology, okay. Is it going to be very difficult if you want to introduce a Schottky diode between base and collector? Let us see how one does it. Okay. Actually the beauty of this is that it is very conducive, all right, to, I mean, it does not make technology very much difficult. Okay. I will just draw the cross section of the bipolar transistor first. The integrated circuit bipolar transistor. So, this is the N plus P, N plus N, N plus, this is P, P, P. So, this is the emitter contact, you have the base contact here, and this is the collector contact, all right. So, this is the integrated circuit bipolar transistor. So, you have an island, okay. I will just draw the top view also, I mean, okay. Because I think to give you the overall picture. So, this is the P island. So, this is the top view, okay. Then you have the emitter, which is like this, all right. Then you have the base, then you have the N plus collector, and so now the contacts, this is the emitter contact, this is the base contact, okay, and you have the collector contact, okay. Of course, you have the buried collector also, which is somewhere underneath, okay, all right. So, this is actually the overall picture. So, this is the P plus, okay. Actually, this is the island. It is like an island, you know, in which you have the transistor. Okay. This is the top view. You are looking from the top. This is the cross section. So, this is from top view. It is actually circular. okay, and then you see the cross section. So, this is an island in which the device is formed, okay, a p-n junction which isolates, which is actually reverse biased all the time. So, that it isolates the different transistors on the same chip. Okay. So, this is the emitter contact, is the emitter contact which is here, the base contact which is here. So, this is the base p region, okay, and this is the n plus collector region, okay, and this is the contact, collector contact. Now, why do you require n plus for collector? Because the metal, okay, which is usually aluminum, say, gives ohmic contact only with n plus, okay. With n type it gives a Schottky contact. Schottky means it is a rectifying properties. So, you would require a ohmic property, ohmic contact here. So, you have to make an n plus here, all right. Now, how do you get a Schottky transistor made? Okay. It is very simple, okay. The only modification that you do is in this circuit is that this collector base contact which you have here, you look at this, okay, you just extend it over the n type collector region, okay, that is all. What do you have here? Here you have metal n type semiconductor, all right. So, this region, okay, behaves as a Schottky diode, all right. Here it behaves as a Schottky diode, the metal semiconductor here, all right. The metal semiconductor, n type semiconductor here behaves as a Schottky diode, okay. So, from the base contact to the collector, so this is the collector region, okay, you have a Schottky diode. So, this is the base, it goes to the base, and again you have a contact to the n type collector, all right. So, just if you go back to this one here, so from the base you have a Schottky to the collector, all right, and you have the normal transistor. So, it is very simple, you know, you just have to extend it. So, basically the collector contact, the base contact has to be extended over the n type collector region. So, that gives you a Schottky transistor. So, technologically, okay, it is very simple, okay, you do not have to do much, all right. It is very simple to convert a normal bipolar transistor to a Schottky transistor. Is it clear? So, all right. So, it's so you see that in a digital circuit, all right, to improve the speed, okay, all right, to improve the maximum operating speed of the circuit, okay, you have to reduce the storage delay time, okay, you have to reduce the storage delay time, and to do that you can, what you can do is you can have a Schottky transistor. So, you can prevent the transistor to go to saturation if you can just make it switch between the cutoff and the active region rather than from cutoff to the saturation region, okay. And that is done, one way to do it is to have a Schottky transistor, okay, which actually does not go to saturation, okay. So, basically in bipolar digital circuits they can be classified, okay, into two categories, okay. I just bipolar logic families, okay. One is called saturated logic, okay, and the other is non-saturated logic. In saturated logic, the transistors are switched between the cutoff and the saturation region, all right. In non-saturated logic, the transistors do not go to saturation, okay. They are generally higher speed of circuits, okay, and the transistors go from cutoff to, they actually go to the edge of saturation, okay, all right. So, the output voltage would go not, it would not reduce to 0.2 volts as such, okay, it would reduce to around 0.4 to 0.3 volts. Okay. So, actually the logic low would go up a little bit, but that is a small price to pay for the gain in speed which you achieve. Okay. So, the examples of the saturated logic are the TTL, okay, and the I squared L. Okay. Whereas, the examples of non-saturated logic, you have the Schottky TTL, okay, where you use the Schottky transistors, and you also have the ECL, emitter coupled logic, where the transistor also does not go to saturation, but in that case you do not use a Schottky transistor, but you adjust the voltages, okay, in such a way, all right, the voltage levels in the circuit in such a way that the transistors actually do not go to saturation. We shall discuss that in detail when we come to ECL, but there also the transistors do not go to saturation. So, these would be obviously much faster compared to the saturated logic family, all right. So, yeah, so this gives you an idea of the different types of logic families. Okay. Now, okay, so basically a classification, okay, based on the whether the circuit is, whether the transistors are going into saturation or not. All right. Okay. So, with that we come to the end of this discussion on switching properties of this bipolar transistor inverter circuit, which is very important. Okay. These concepts which we have developed, okay, all right, when discussing this is very important in understanding basically the delays, okay, in any logic circuit. So, okay, if you have understood this very clearly, all right, then one can very easily appreciate, okay, the different delays, okay, I mean the different delays in the different logic families and how one is different from the other, okay, all right. Okay. So, actually now before going into the logic families as such, I will just one topic we shall take up, that is the different characteristics of logic families. Okay. That is, when you take up a logic family, what are the different properties by which you can actually characterize a logic family? What are the different specifications you talk of? That is, suppose you want to make a distinction between two logic families, you say that this logic family is better than this, okay, but you cannot, this better is a very vague term, okay. So, you have to say in terms of certain characteristics, all right, better or worse or this, you know. So, what are the different characteristics or figures of merit, whatever you call it, okay, of these logic families, okay. We just have some idea of that before we actually go into the logic families, so that we can discuss that them in terms of these characteristics or specifications, okay. All right, the different characteristics or specifications or figures of merit, okay, characteristics or specification, I think specification is a better word, specifications of they are propagation delay, okay. That is, it gives you an idea of the speed of the device, okay, speed of the logic circuit, how fast or slow it is. So, propagation delay, there are other there are also some other things related specification. They are called rise time and fall times, which is also, okay. So, this propagation delay, rise time, fall time, they all relate to the delay component of logic circuit. So, we shall come to these definitions, okay, that is very important before we actually go into this discussion. Then power dissipation, okay. Power dissipation is also very important nowadays. In fact, it has become very important, okay, the characteristic of a logic circuit, because of the fact that the trend nowadays is to pack in more and more circuits, okay, or more and more components in a given area. You make the devices smaller, okay, so you are having more number of components in a given area. So, the power dissipation is actually going up in a given circuit, okay. So, that puts a limit on the packing density, okay. So, one has to really think about power dissipation, okay. So, we shall see about power dissipation. In fact, we shall also see how these two are related, okay. It is not they are related, as we had seen when we put on the curve, that with the current, okay, if you increase the current, the delay goes down, okay. Of course, it becomes a constant, but if you increase the current, you are also increasing the power dissipation, okay. So, if you increase the power dissipation, there is a possibility of reducing the delay. So, they are interrelated. In fact, all these characteristics may be sort of interrelated, all right. So, you have propagation delay, you have power dissipation, other is noise margin, okay. That is, it gives you an idea of how much noise a circuit can tolerate, all right. So, that is also very important, okay. And also the other important thing is fan out, okay. That is, fan out means fan out, fan in also to some extent. That is, if you have a gate, okay, that is, say for example, if you have a NAND gate, all right, a 2 input whatever is a NAND gate. So, this output, okay, can be fed as input to subsequent stages of gates. So, how many outputs can you connect to this gate, okay, that tells you about the fan out, okay, all right. And so there is a limitation, okay, because if you go on increasing the fan out, the characteristics, the other characteristics, okay, starts getting degraded, okay, the speed may fall, okay, all these things, okay. So, again there is a limit, all right, on the fan out. So, all these things are very important characteristics of logic families, and so when we discuss one with respect to the other, we have to discuss in terms of these specifications, okay. And so, we shall take next class, we shall take this up, okay, give you the proper definitions, okay, and then we shall move on to the actual circuits, okay. We shall take up the logic actual logic circuits, okay. We shall start with TTL and then go to I squared L, ECL and all that, okay. All right, so we shall stop here today.